So by now you already know what derivatives are. You know how to take derivatives. And you also know what the derivative tells us. Well, sort of. You know that it's the slope of the tangent line, and that's pretty much it. And if that's your understanding, then that's completely fine. So if that's your peak understanding, then, well, that's a good place to start. But you should start really asking what these tangent lines actually tell us. So take a look at a function f like this, and look at where the local extrema occur. Now ask yourself how we can find them. Now let's compare this with f prime, the derivative of this graph, and notice that every time that the function hits a extrema, the derivative hits 0. There's a horizontal tangent. The function f is also increasing whenever f prime is above the x-axis, or whenever f prime is positive. And this vice versa goes for when f prime is decreasing. So, using this knowledge, let's take some function and let's find the local extrema. Take the derivative of the function and set f prime equal to 0 to find out for what values the function f has a horizontal tangent. Once you have a factored form, because most likely you're going to be asked to solve a question regarding a polynomial, simply solve for the two solutions and do something called a sign chart. Analyze each individual product. So for x equals 0, you're going to analyze y equals x. And note that it's negative until 0 and positive for all values after. And the same goes for 2/3. It's negative until you hit x equals 2/3 and positive for every value after. And just like it is in f prime, you're going to multiply these two sign charts. The dotted lines represent negative values and the filled in lines represent positive values. When you have an interval here where you have negative and negative, you're going to multiply them together to get a positive value. Positive times negative values always result in negative, so that interval there is negative. And you're always going to compare values and intervals in between and away from critical points. So this is exactly what you're finding. You're finding that the derivative is positive until 0, negative from 0 to 2/3, and positive for every value thereafter. So your sign chart definitely works. Now, whenever f prime changes signs like you see from plus to minus or minus to plus, we call those critical points, and those are where local extrema occur. And intuitively, when it changes from positive to negative, it's a maximum, and vice versa for a minimum. Now, let's take another function here. We can analyze more about some functions using derivatives. We can in fact figure out when functions are concave up or down. For all values from left to right until this point, the function is concave down. It has a frowny shape. And for all values after, it's concave up. It has a smiley shape. That's how you think about concavity. Now, we can analyze concavity, just like we did for local extrema, by looking at the second derivative. Not the first, the second. Simply set the second derivative equal to 0 and find critical points for the second derivative. In this case, you'll notice you'll do a sign chart, neg to pos, and it follows just as nicely. Whenever f double prime is negative, we have concave down intervals and vice versa, and points where concavity changes from neg to pos or pos to neg, those are called inflection points. We can even use this to find maxes and mins. See, this is what we call a second derivative test. Earlier, we did a first derivative test to find local extrema. Now we're going to do a second derivative test by comparing sign charts. Compare both f prime and f double prime. On any interval where f is concave down, all critical points in that interval are going to be maximums, and any concave up intervals, well, any critical points in there from f prime are going to show minimums, and you can find out intuitively why. Now, let's do another test. This is the last test we're going to learn today, the candidates test. So we have the function f as given, and we're given a closed interval. So we're not considering the entire function as continuous domain, just a closed interval. Now, for any maxes and mins, we have to consider the endpoints as potential candidates. So do the standard first derivative test, find the critical points with the derivative, and include the endpoints. And now plug in all of your candidates back into the function and compare the values of f at each of those points. And simply here, whichever one's the largest is the maximum, whichever one's the smallest is the minimum. So maximum occurs at f of 2, and minimum occurs at f of 0. Now, I believe this is a lot easier to explain with handwritten notes, so I want to just make sure that you guys really understand what's going on here. If we have a function that is concave down, so it looks something like this, okay? So we have a max here and a local min here. If it's concave down, no matter what, values change from positive to negative. It's increasing and it's decreasing. It creates a concave down shape, an upside down U. So it's going to be a point where the tangent is above the graph, and thus it is a maximum. But if you have a point that's decreasing, stops, and then goes back up, like a parabola, or like a U, a smiley face, well, this is going to be a minimum. And so that's why the second derivative test works. When you have f double prime is greater than 0, and f prime is equal to 0 at that point as well, this combination gives us a minimum. We have concave up, so it's a minimum. So think backwards for the second derivative test. But for f double prime less than 0 and f prime equal to 0 at that same point, that same x value, you're going to get a maximum, even though it's concave down. Now, this is the second derivative test. I also want to note that everything you did earlier to find the values for which f prime of x is equal to 0, and you get critical numbers, this is what you call the first derivative test. The first and second derivative test will only tell you where there's local extrema or concavity changes. But the candidates test will tell you on some closed interval that there is a max or min, because when you have a closed interval like this, there's, by the extreme value theorem, an absolute max and min on this interval. So that's just to clear up some things, and I hope that this helped you out a little bit to understand the point of this video. There are 3 tests that we learned: the first derivative, the second derivative, and the candidates test. So hope that helped.